Hey guys, welcome back to AlgoYogi. We are doing tree series right now. So let's move on to our next problem in the series, which is maximum width of a binary tree. Let's go to the problem on LeetCode. The description is, given the root of a binary tree, return the maximum width of the given tree. And maximum width of the tree is basically among all the levels they're asking us, not just the last level or any level. It could be any level, and it needs to be the maximum width. Now, maximum width of the binary tree is defined as, on any level, it's the distance between the leftmost and the rightmost node on that particular level. So on level 1, it's just one node, so the width is 1. On level 2, it's 2 nodes, 3 and 2, and the width would be 2 on level 2. On level 3, it's 3 nodes, however, the width is 4 and the answer is also 4. Why? Let's understand. So if you see in the first example here, on level 4, sorry, not level 4, level 3, so this is level 1, level 2, level 3. If you see, there was supposed to be a node over here, which is null right now. And as per the definition, it says it's the distance between the left and rightmost nodes. So it's leftmost and rightmost node on one particular level. And that is the reason the answer here is 4. Maximum width is 4 for this example. Similarly, for example 2 as well, when we are calculating the max width, we will have to consider that there were supposed to be certain nodes which are basically null right now. However, like when we are processing our tree using breadth first search or depth first search, we cannot process null nodes because they wouldn't have any left and right nodes. So let's go over this example first. So this was supposed to have a children at this level, and that would have been less. The value does not really matter, so let's just assign x, and here as well it was supposed to be x. So these two are missing, left for this and right for this. Now similarly, 5 was supposed to have a child over here, which is right child, and this was supposed to have a child over here, left and right, and this was supposed to have 2 child over here. Now in that case, this was supposed to also have a child over here. However, they are not present because it's not a complete or full binary tree, but the width will still exist. And the way we're going to calculate is we find the known null node on that level. So this is the last level. This is also a level, and it could have been a case when if this didn't exist, only this existed, then the root, basically the width would have been just 2 for here, but that's not the case, so let's not go over there. Now in this example, we find out the leftmost non-null node is 6, and on the right side, rightmost non-null node is 7, but they were supposed to have these nodes in between which do not exist. However, we have to consider them while considering the width, because if you see this level, this whole gap was left empty, and the way we have seen it in the definition, this is how we're going to calculate. So r minus l plus 1, which is basically the index of rightmost minus leftmost plus 1. And what do I mean by indexing? Let's go over this. So in a binary tree, we can calculate the indexes because tree is represented, or one level or tree, binary tree is represented as an array, and basically null values are basically placed as null over there. Now if I had, let's say, a small tree like this, let's call it x, value don't matter. Now if this was supposed to have an index 0, then left child can be calculated by doing left, basically index into 2, and right child can be calculated index plus 2 plus 1, index into 2 plus 1. So that's how we can calculate the right and left index of a binary tree. Now this value could be 0 or it could be 1. In both cases it will work, and the reason it will work is because next time once we move on, so if this was 0, this will become 2 into 0 is 0, but this will be 2 into 0 plus 1, so this will be 1. However, if you see on this level, now we have 0 and 1, but if we were calculating another level, this should give us right answer. So this will be 0, this will be 1, this will be 1 into, basically 1 in, it's not 1, it's the index, so 1 into 2, which will be 2, and this will be 1 into 2 plus 1, 3. So it doesn't really matter if we assign 0 or 1 here. It's on that particular level we will be basically calculating the difference. So it will be 3 minus 0, which is 3 minus 0 plus 1, so that would be 4. So I talked about this case right here, so don't confuse yourself. So it's I calculated basically for this level. Now this is pretty easy to understand, that on each level, because this will help us avoid processing these null nodes. However, calculate each level and their indexes, or each node and their indexes correctly. So this will basically be, if I take an example, let's say this example 4, 3, 5, 6 and 7. So in this case this would be index 0, and this time we will be using BFS algorithm. Is just while putting nodes in my queue, I will also put the indexes also next to the node. So in my queue I will place 0 and 1, so basically like that in my queue, and then I will pop it out from the queue, and then I will basically assign, I will find out the next left and right indexes for this level's nodes. That would be again 0 and 1, so it would be 2, 0 on this level. And the way I process this queue is basically processing level by level. So this, I will take the snapshot of this and then start processing this, and then next time it would be 4 and 1. I take the snapshot of this and I just process this. Next time I will place all its children into an empty queue, and then next time I'll process that. Okay, so let's go into implementing the solution. This will be a big of n time complexity, because we are only processing each node once. Okay, it will be really clear when we write the solution. So this is what I meant. We're going to have, let's call if root is none, we just return 0, then there is no width. Otherwise, let's have a variable called max width. Max width is 0 initially, and then we're gonna have our queue because we are using BFS. And this time I said I want to have the root and initially the index 0. Okay, because this time I want to process the nodes using the index, so that using those indexes I can calculate the length of basically the width of a particular level. So this is how we do it, while q. And let me basically take this snapshot of this queue. Snapshot means like I'm just taking out all the values of that particular level so that I can process them all together, rather than keeping a check how many values on one particular level were. Some people like to do it just using this queue, but I think this makes the code like really clean and simple, and it's easy to understand, and like this. Now what I want to do, I want to calculate the max width by what? Before that, let's just have a node in node and index. So let's just do index, I think node and index. So that's how we have it, like root is the node and in 0 is the index. So root and index in queue. So if node exists, then I'm placing it inside my big queue. So queue dot, so if node dot left, so I'm gonna place either left and right. So queue dot append, and I want to append what? I want to append node dot left and the index. How am I calculating the index? Using the parent index into 2. That's how we did it. And let's do the same for right child. If, sorry about that, if right, then put the right child in the queue. So we have to process that, and it would be at index 2 into index plus 1. Okay, now finally once we come out, we have processed all the levels and all the nodes, and we will return our max width. But what's missing? We haven't updated our max width. And how are we gonna do it? We only put null nodes onto our next level, which is queue, to process. It's just I have to update my answer as well. So max width would be maximum of max width, or I take out the rightmost, so that would be from here, rightmost element from my queue, which is an array right now, or list, and the index, which is at first element, minus the first element of my queue and its first element. And I have to add 1 because that's how we calculate it. It's going to be for index 1, it will be just both elements are same, so it's 1 1 1 minus 1 is 0, but the width is basically 1, so we have to add 1 when we are calculating the difference. And this seems okay to me. Let's run it. Let me zoom out and let's try to run our examples. Okay, this works fine. Let's try to submit it. All right, let's write the time complexity. Now I think you guys can already tell that we are iterating each node once, so time complexity is going to be big of n. N is the number of nodes. Space complexity is basically if there are n nodes on one particular level, we are going to have just that many nodes. So it's actually the max width is gonna be the space complexity. However, I think in worst case we can just say 2 into n plus 1, so it's going to be big of n, right? Space complexity. So this is what I meant, like big of 2 into n, or I think we can say the index or h height, so log n, but log n in worst case could be n also, but that is because if binary tree has like all just 1 1 1 level, so you know You just keep placing all of them, but I think in that case also this will be big of log n. So I think the time complexity will be big of log n, which is h, height. All right, let's go back to AlgoYogi, mark this problem solved, and see you guys in the next problem.